Hello and welcome students. Today is our lecture number 52 and we are going to conclude this topic today with two more numericals. You can see in this chapter till now we have discussed about the bending stresses. Bending stress is subjected to UDL on the beam or bending stress is subjected to point load on the beam. The beam may be simply supported or cantilever. Furthermore, we have studied about the various cross sections like rectangular cross section, circular cross section, hollow rectangular section. Even today we will discuss the hollow circular section also. And we will discuss some practical numericals too, like hollow pipes, what happens when the water is running from the pipe, which type of bending stresses are induced in the pipe when the pipe is full of water. Okay, so for that our main bending stress equation or flexure equation is sigma is equal to mi by z. Okay, so you can see this is our chapter going on and we will conclude this topic today, and from tomorrow onwards we will start the composite beams, means I section, T section, etc. Till now we are going with the simplified sections only, like rectangle or circular. Let us see some example. Example number 14.16, you can see a hollow steel tube having external and internal diameter of 100 mm and 75 mm respectively. So this is the pipe. You can see steel tube hollow having external diameter is this much, means 100 mm, and internal diameter is 75 mm. This is the front view having length 5 meter. You can see simply supported over a span of 5 meter. So actually this pipe is acting as a simply supported beam. So here it is reaction RA and here it is reaction RB. These are the two end points of the tube. Now the tube carries a concentrated load of W at a distance of 2 meter from the one of the supports. From one of the supports, so you can take from the right side or you can take from the left side. In our figure we have taken from the left side. At a 2 meter distance the point load W is acting and 3 meter remains as it is. What is the value of W? If the maximum bending stress is not to exceed 100 megapascal. So we have to find W for the maximum bending stress 100 megapascal. The distances are covered in 10 raised to 3 mm. Okay, diameter is given to you. Internal means small d, external means capital D. Now what is the distance for this 100 mm? For this 100 megapascal. Now this distance BC is most important, 5 minus 2, 3 meter, 3 into 10 raised to 3 mm, which is written over here, and the maximum bending stress is at the outermost surface 100 megapascal like this. Okay, this is the bending stress distribution diagram. At the center of gravity of the section the bending stress is 0 and gradually increasing up to top layer and up to bottom layer as well. So now we are interested in finding the concentrated load W, which is acting eccentrically. See, when the load is acting like this, 2 meter from the left side and 3 meter from the right side, then this type of load is known as eccentric load. You may check in the SF diagram, BM diagram, or in the support reaction also. So for this type of eccentric load, the distance 2 meter is known as A, small a, and the distance 3 meter is known as B, small b. And the total distance 5 meter is known as L, length of the beam L, 5 meter. So this is going to be a bending moment formula like this. See, this is the most important. Bending moment is equal to WAB by L. When this type of W, means point load, is acting eccentrically at a distance of A from the left side, B from the right side, and the total length of the beam is L, then the resisting moment is given by WAB by L. So this is the standard formula which you have to remember. So replacing the values, W we have to find. A means left side distance 2 10 raised to 3, right side distance 3 10 raised to 3, and the total length 5 10 raised to 3. So final answer will be 1.10 raised to 3 into W. So this is the bending moment. Now as we know, section modulus for the hollow circular section, this is another formula which you have to remember. For the hollow circular section, it is the pi by 32 d in the bracket d raised to 4 minus d raised to 4. This is the standard formula for hollow circular section for the section modulus. So just replacing all the values, Capital D means outer diameter is 100 mm while the inner diameter is 75 mm. So replacing the values and solving in the calculator, you will get the answer of Z as 67.1 into 10 raised to 3 mm cube. So this is the section modulus. Bending moment is available in terms of W. Section modulus is available as a value of 67.1 into 10 raised to 3. So now, as per our standard equation, sigma is equal to m by z. This is the equation of bending stress. So sigma is already given in the data 100. M is equal to 1.2 10 raised to 3 W, which we have calculated in terms of W. And Z will be 67.1 into 10 raised to 3. So answer is 0.018 W. So now W, by solving, we will get 5.6 into 10 raised to 3 Newton. So it is 5.6 kilonewton. So this is the point load W, 5.6 kilonewton. So this is our numerical number 14.16, in which steel tube is given to you of hollow diameter 100 mm external and 75 mm internal. Now let us see one more numerical, which is a very practical numerical. You see, very practical numerical, and which is most important, 14.17. You can see what is given in the data. A cast iron water pipe of 500 mm inside diameter and 20 mm thickness. Now here it is outside diameter is not given. 500 mm you can see it is the internal diameter. And the thickness is 20 mm given. So thickness 20 is to be added at the top and at the bottom also. So this is the thickness 20 mm at the upper side and 20 mm at the downside. So total will be 540 mm outside diameter of the pipe. Now it is simply supported over a span of 10 meters. So you can see here there are two supports RA and RB over a span of 10 meters. When the pipe is running full, now remember this thing, the pipe is running full means pipe is carrying water throughout the length. So you have to understand that the pipe is subjected to UDL now, as the pipe is running full of water. Now UDL is also two types of UDL. First one is UDL of the entire weight of the pipe. It is W1, which denotes the weight of the pipe per meter length, while the second UDL is weight of the water flowing from the pipe. Okay. So that is W2. It is the weight of the water through the pipe per meter length. And density of the water is given, and density of the cast iron material is also given. 70.6 kilonewton per meter cube and 9.8 kilonewton per meter cube for water. So it is kilonewton per meter cube. So by converting into Newton, we have to multiply 10 raised to 3. And for meter raised to 3 into mm raised to 3, it will be 10 raised to minus 9. You can imagine at your own, or you can do rough work in your notebook. So final answer will be 9.8 into 10 raised to minus 6 Newton per mm cube. Here it is not square, it is cube. Similarly over here 70.6 into 10 raised to minus 6 Newton per mm cube. It is the density in Newton per mm cube which we have required in the calculation. So in the calculation we are taking all the values in mm only. So this is very most and very dangerous numerical. We are wanted to find UDL first, which is acting on the pipe or on the beam, which is simply supported. UDL first is W1 of the weight of the pipe, W2 for the weight of the water, and adding W1 and W2 we will get the total UDL on the pipe. So let us now see the calculation. As first we are starting with the cross section area. The hollow pipe is there, so cross section area will be pi by 4 d square minus d square. So it will be pi by 4 capital D square minus small d square, which answers 32.67 10 raised to 3 mm square. And its weight W1 is equal to 70.6 into 10 raised to minus 6 into 32.67 into 10 raised to 3. How this weight comes? You can simplify, or if you have studied the physics, then if you will multiply the density, okay, if you will multiply the density with the area, then answer will be Newton per mm cube into mm square. So it will give you the weight W1 in Newton per mm, means it will give you the UDL due to weight of the pipe, that is 2.31 Newton per mm. So you just remember this. If you wanted to find the weight of the pipe in UDL, means Newton per mm, then you must multiply density with the cross section area of the pipe. Remember, this is the cross section area of the pipe. But when we are finding the weight of the water only, then we have to take the cross section area for the water only. Now water is running from the inside diameter only, so we are taking cross section area of the inside diameter only, that is pi by 4 small d square. So pi by 4 500 square, which will give the answer of 196.35 10 raised to 3 mm square. So its weight is W2 is equal to density into cross section area again, that is 1.92 Newton per mm. Now the total weight W is equal to W1 plus W2, which is 2.31 plus 1.92. Answer will be 4.23 Newton per mm. We also know that bending moment is equal to WL square by 8 for the UDL. Okay, so the total W is equal to 4.23 Newton per mm as we have calculated with the help of weight. Now length is given as 10 meter, so 10 into 10 raised to 3 whole square will be as it is upon 8. So 52.9 into 10 raised to 6 Newton into mm. So this is the bending moment. Now we are interested in calculating the bending stress. So now section modulus is pi by 32d into d square minus d raised to 4. Here it is again the printer mistake, d raised to 4 will be there. So pi by 32 into 540, external diameter, internal diameter we have calculated with the help of thickness of the pipe. So now section modulus will be 4.096 into 10 raised to 6 mm cube. Now we are wanted to find maximum bending stress. So what is the equation for bending stress? Sigma B maximum is equal to m by z. M means bending moment, which we have calculated earlier, 52.9 into 10 raised to 6. In the section modulus right now we have calculated 4.096 into 10 raised to 6. So answer will be 12.9 Newton per mm square. So it will be 12.9 megapascal. So this is the final equation of the bending stress. So this is very practical numerical in which the water is flowing from the pipe and we have to calculate the stresses on the pipe. So we have calculated the bending stress 12.9 megapascal. So from this value we can imagine that the cast iron pipe is suitable for the flow of water or not. If some other liquid is there, density will be changing. If the density of the liquid is changing, which will affect the pipe material, which will affect the value of the stress. So accordingly, we have to select the material of the pipe. So this is very practical numerical in which through which you can just made a justification that which type of material should be used to form a pipe, whether it is a PVC pipe, whether it is a stainless steel pipe, or whether it is a cast iron pipe. So students, from this type of numericals you will gain your practical knowledge as well. So from the tomorrow onwards we will start a composite beams, means beam having different types of cross sections like T sections, I sections, or simply supported beam, UDL, point load. All the combinations will give you the different types of bending stress. So that type of sums are going to be very tough. So till then you just practice these numericals. We will start again on tomorrow. Goodbye students, till then thank you very much.